So now I want to look at the P-Series Theorem. And so I'm going to prove it by answering this question. For what values of P does the series 1 over n to the P converge? Now, let me first point out that we've actually already looked at the case that P equals 1. If P equals 1, then what we have is the series 1 over n to the first, which is the harmonic series. And in a previous video, I showed, using the integral test, that the harmonic series 1 over n diverges. The way that argument goes is, this is a positive, continuous, and decreasing expression, 1 over n. If you integrate 1 over x, as x goes from 1 to infinity, antiderivative is natural log of x, which is increasing without bounds, so the integral diverges, so the series diverges. Okay, so let me write a little number line up here. So this is our P line, our P axis, keeping track of the values where this thing either converges or diverges. So we already know that at 1, the series diverges. It does not converge when P equals 1. Okay, here's another specific value. What about P equals 0? If P equals 0, then we have a non-zero base, because n is 1 or bigger, raised to the 0 power. This is really just becomes the constant, a sum of just 1 here, if we have n to the 0. So that's 1 over 1. That's just, so that series, P equals 0, we basically have just 1 plus 1 plus 1 plus 1. That's not approaching any finite number. This is just increasing without bound. Also, if you want, you could apply the nth term test for divergence. So the limit of the terms in this series approaches 1 if it's constant. And so, the limit approaches 1, which is not 0, so it diverges by the nth term test. So it diverges when P equals 0 as well. Okay, I'm going to need an eraser. Where did it go? Here it is. Sorry. So now let's consider any negative value for P. I'm going to stop picking just, one number at a time. That's good. That would never work here. Let's say that P is any negative number. P is less than 0. Then, when we're looking at this series, if P is negative, so this is some negative exponent here, then the natural thing to do would be to move that expression to the numerator. Oops, move it to the numerator, so I shouldn't be writing 1 over anymore, and make it positive. So if I move this up, then what I'd write here is negative P. But keep in mind, if P is a negative number, then this negative P, you're going to have negative and then a negative number. This will be positive now. This exponent right here now is positive. And so you have n raised to a positive exponent. You could apply the nth term test to that. So the limit, as n approaches infinity, of n to the negative P, but this is tricky. You have to keep in mind that this negative P now is a positive number. So n raised to this positive exponent, that's going to approach infinity. And since the limit is not 0, then by the nth term test, again, nth term test, this series will diverges. So it diverges for all of these negative values of P. So now we can consider strictly positive values of P. And so now you're starting to wonder, well, does it converge anywhere? We know it diverges for all P less than or equal to 0. It diverges when P is equal to 1. So now let's consider P is greater than 0 and not 1. P not equal to 1. Oops, to 1 here. Okay. Then, well, let's look at the series. This expression now is positive, continuous, and decreasing, if p is positive, for all x, here, if I write it as a function of x here, x to the p. This would be positive, continuous, and decreasing for all x greater than or equal to 1. So we can apply the integral test. If we apply the integral test, so the integral from 1 to infinity of 1 over x to the p, then this is the limit as t approaches infinity of the integral from 1 to infinity of, instead of writing 1 over x to the p, I'll write it as x to the negative p. Okay, and so to integrate that, I can apply the power rule for antiderivatives. So that'll be x to the negative p plus 1 over negative p plus 1, evaluated from 1 to t. And so this, written another way, is the limit as t approaches infinity of, I'm not going to fit it here. Let's look at it here. So the limit as t approaches infinity of t to the, instead of writing negative p plus 1, I always like to have the positive term in front. So I'm going to write this as 1 minus p, positive 1 minus p over 1 minus p. Sorry for the background noise. Okay, minus, if I plug in 1 for x, I have 1 to the 1 minus p over 1 minus p. Okay, which, whatever value of p, keep in mind, we already dealt with p equals 1, so it's safe to assume p is not 1. So this is some finite number here. And so the convergence or divergence is going to be determined here by this limit. So let's look at that limit. Let's see, I'll write it here. So I'm going to copy that step up to here. So it turns out that the convergence or divergence of this improper integral comes down to this limit, t to the 1 minus p over 1 minus p. Okay, and then minus, we decided this is some finite number over here. I'm not really worried about what it is. Because remember, it doesn't, we don't care what this improper integral converges to. If it we just care about if it converges or if it diverges. Okay, so here we actually need to consider some individual scenarios. If p is less than 1, and we're already assuming that it's positive, so it's bigger than 0. Let's see, so if p is a number between 0 and 1, then this t to the 1 minus p, this is a positive number. And so you have t raised to some positive exponent, that's going to go to infinity. And so the integral diverges, which means the series diverges. So that means between 0 and 1, this limit's going to infinity, the integral diverges, so it also diverges between 0 and 1. So now our only hope is for p's bigger than 1. If p is strictly greater than 1, then again, let's inspect this limit. So limit as t approaches infinity of t to the 1 minus p over 1 minus p. If p is greater than 1, then this right here is a negative exponent. Negative, which means if I see a negative exponent, I would move it to the denominator, make it positive. So t approaches infinity of 1 over, so we've got this 1 minus p down here. We're not so concerned with that. And then we bump this down. So times t to the, when we change the sign on this, so negative 1 minus p is p minus 1. Sorry, that's kind of small there. And again, we're assuming that p is a number greater than 1. So here, I moved it downstairs and I made it positive, which in general, I mean, this is a useful little rule. If you've forgotten, negative a minus b is equal to b minus a. And so that's what I'm doing here. Negative 1 minus p is p minus 1. And so this is now raised to a positive exponent. So this has the form 1 over infinity So it's going to 0, finite number here now, finally, which means the integral converges. I'm sorry, I've run myself out of space, but when p is greater than 0, we're going to end up with when p is greater than 1, we're going to end up with a limit of 0 here, which means that the integral converges. We're going to get a finite number overall for that improper integral. So it turns out that it only converges when p is strictly greater than 1, which that right there is your P-series theorem. But it's a consequence of the integral test, that the series, P-series, so any series of the form 1 over n to the p, converges when p is strictly greater than 1. That's the answer. That's the result given in the P-series theorem.